Hey guys, happy Tuesday. So we are going to go through how we're going to solve multi-step acceleration problems today. And really this is where I think physics gets a lot of fun because everything we've done so far is pretty straightforward. There are a couple of things that you have to remember to look for here and there, like making sure our units are checked or that our directions are matching up the exact same. But this is where it becomes kind of like a fun little puzzle and you're trying to piece together all of the things that you need. If everything was like super straightforward, first of all, it would be a lot less fun, but we'd also have all the answers. So physicists and mathematicians are really great at trying to make sure that we can figure out how to do all of it together. So we're going to go through the notes on these and some of the example problems. Actually, I don't know if there's a ton of notes on here. It's mostly example problems. We're going to be using your 5 kinematic equations. So if you have that, or if you need to reference the PDF that's in Classroom, it is there, so you have all of those. I would write those down on maybe a separate piece of paper or a note card so that they're always handy for you. All right, so let's start with problem number 1. We have a straight 1 kilometer track, and we have a race car accelerating from rest to its top speed through 325 meters west at 3.5 meters per second squared. And the car then decelerates at a rate of 1.9 meters per second squared east to a complete stop. Will the car stop before the track ends? So let's go ahead and look at all the different information they've given us in this problem. So we have 1 kilometer track. I want you to be red. There we go. Red. So a 1 kilometer track. So our distance is 1 kilometer. And we're accelerating from rest. So our initial velocity is 0. And we're going at our top speed through 325 meters west. And that's a weird way to say it. So we have to kind of look at the units to piece together what that means. So 325 meters west is actually going to be like our first distance. And we'll talk about why we're doing that in just a second. And we're going at 3.5 meters per second squared. Again, it's not super straightforward, but the meters per second squared tells us that that's our acceleration. The car then, so when it tells me then, it looks like I'm going to have a 2-part problem here. And we're decelerating at a rate of 1.9 meters per second squared east. So I'm going to go ahead and make this acceleration negative because it says I'm decelerating. So negative 1.9 meters per second squared. And because I made it negative, I'm still going to use west as my direction from the first part. So that's how I can kind of balance those two things out. And we're coming to a complete stop. So at the very, very end, we have, I'm actually going to say V3 because that is where we're ending the second place. So we started at 0, then we accelerated. We're actually going to have a top speed over on our first half that we haven't figured out, then that'll be V2, and that'll be where we started over here. So we don't know this information. Will the car stop before the track ends? So we need to figure out the distance that it's ending at. So it's a really complicated looking thing when we just look at the numbers. So what we're going to do is go through these different strategies. So first we're going to draw a diagram of the solution or of the situation. And again, please do not feel like you have to Google how to draw a race car on a track. This, I don't care if you do circles and lines or whatever, but you need to be able to kind of visualize what's happening on paper. So we're going to use V1, V2, V3 for our different velocities, which is what we talked about when I was writing down all the information from the problem. We're going to solve it in parts. So our V2 is going to be our final velocity for the first part where we know that we're accelerating. And then it's also going to be our initial velocity for that very end part where we're decelerating. And we don't want to use V1 and V2 and then for the first part and then V1 and V2 for the second part because it's a little confusing. So we're just going to add in a V3. We can kind of make up those rules because it's just really identifying to us what each of those values is. And then we need to solve for our final displacement and compare the two displacements, so from when we're accelerating to when we're decelerating and stopping, to see if we fit that 1 kilometer track. If we don't, that's a problem. So here's kind of what it looks like in picture form. We have starting from rest, we're accelerating through 325 meters of the 1,000 meter track. So this was changed from 1 kilometer over to meters so that we're going to keep the units consistent. And we need to solve for V2. Then on the second half, we start at V2, we end at a stop, and we know what our deceleration is, but we need to figure out how long this part took so that we can see if we're still on track at the very, very end. So we're going to use a couple different equations to go through this. We're going to start with equation 5, which is our V2 squared equals V1 squared plus 2A delta D. And so when we plug all of that in, this is for our initial part 1, so when we're speeding up. So I have 0 at my start, so I can kind of ignore all that that's going on. And then I need to make sure that I go ahead and do the math on all of this. And remember that I have my squared. Don't ignore the squares because that's not going to help you a whole lot. So when I do this, I get 2 times 3.5 times 325 because that's the distance that I went when I was speeding up. So V2 squared is 2275. And then I need to square root that. And because I'm square rooting it, you technically get a positive or negative answer. We know, though, that we're speeding up, so we know that we're going to have a positive number. So my final velocity at the end of part 1 is 47.69696 meters per second. In this instance, we're still heading west because we knew we were speeding up, and it's a positive number. So what you'll see on the next slide is it says to go ahead and save this number in your calculator. Because we're going to use this number for part 2 in a graphing calculator, you can actually like copy and paste or save the number so that you can use the exact full decimal later on. We don't really have that. So as long as you round to where you feel comfortable, this is a weird number to round because it all kind of rounds up. So I try to take at least 3 decimal places, and then I would round this up to be a 7. So I would leave it off as this. You can always go back and like choose previous answer in your calculator if you really want to. But this is about as accurate as we're going to really need right now to measure. So now we need to figure out how far we're traveling on the second part, so when we're decelerating. So I'm going to put that number in from my part 1. And they changed it over to saying V1. I would still personally say V2 and V3 because it's just going to be easier to keep everything straight when you're looking at it all at once. Because when you're putting just the, hold on. Okay, so my V2 from part 1, and then I know it's kind of blocking it down here, but this is my acceleration. And remember, we're making it negative because we're decelerating, which means that technically we're accelerating in the opposite direction. So now I'm going to go and use the exact same equation that I just did, but this time we have all the information except for the displacement of the second part. So I plug in all of my information. My V2, we're coming to a stop, so that's 0, so I don't have to worry about that. And then the other thing you have to make sure you're doing is keeping an eye on that minus 47.6969696 squared. So that is actually going to end up being the same thing as saying plus a negative, right? But we're going to square, no. Okay, so my final velocity, I'm coming to a stop, so that's going to be 0. So I don't even have to worry about that part of the equation. The next thing to make sure that we're doing is this negative sign is not a part of the squared. The squared is only affecting this number right here. So we need to just leave that negative sign alone and square our 47.69696 and then leave that negative in front of it. So if I do that, I get my 2275 from before, have my negative sign. I don't know why I wrote it there. Let me write down over here. So I get negative 2275 divided by my 2 times negative 1.9, negative 3.8. So then I can go ahead and do that math. Nope, there we go. And my total displacement for part 2 is 598.68 meters. So once I've solved that, I know how long it took me to decelerate. I have to go back and add together how long it took me to accelerate plus decelerate and figure out what's happening. So the 325 they gave me in the problem plus that 598 that I just calculated, add them together. And yes, our race car will still be on the track. So yay, everybody. That's exciting. Love a happy ending. Okay, so let's go through example 2 now. So just as a traffic light changes to green, a Mustang drives through the intersection at a constant velocity of 14.2 meters per second north. A Camaro that was stopped at the light accelerates from rest, so this is saying the exact same thing, at 2.9 meters per second squared north, so they're going the same direction. That's a good thing. How much time before the 2 cars meet again? So if we're meeting again, that means that our distance for the Mustang is going to equal the distance for our Camaro. And then we want to know how far that distance is. So we're looking for how much time, which means our time is our unknown. So I'm going to break this information into my 2 sections again. First, I have my Mustang. So it's going at a velocity of 14.2 meters per second north. And I can label this V1. It's also going to be V2 because I'm not changing my speed at all, which means my acceleration is nothing. I'm not accelerating at all. I'm just going that same exact pace. And then my Camaro was stopped at the light, so its initial velocity was 0, and it's accelerating from that rest at 2.9 meters per second squared north. And how much time before the 2 cars meet again? So I want my distance for my Mustang and my distance for my Camaro to equal each other, and then solve for that time that it's going to take to do it. So let's go through the steps of how we're going to make sure we have all the information for this problem. We're going to draw a diagram. So being able to kind of visualize what's happening with each car is going to help us to understand if our answer is valid or not. We're going to write the unknowns and unknowns for each car, which we just did. We're going to have our, displacement and time being the same for both cars because they're going to cross paths at the same time. And we're going to go ahead and isolate our displacement value and sub it into another equation. So this is like a systems of equations that you would get in algebra. Algebra 1? I'm trying to remember. Anyway. And we're going to go ahead and rearrange it so that we can solve for our time. So here is all of their information with their drawing. My Mustang is just going to be able to My Mustang's going to be able to keep driving straight through the light while the Camaro was initially going faster, so it had to stop before it drives. So the Mustang is on cruise control. It's set. We're good to go. We just have to see how long it takes the Camaro to catch up to it. So here's the equations that we want to use for each of the parts. So there, 1 is representing the Mustang, 2 is representing the Camaro. Because I have such simple information for my Mustang, I know my constant velocity, I need to figure out my displacement and my time, then I can literally just use the easiest of all equations. Now, this is not any of your 5 equations of kinematics because this is the simplest form that all those are derived from. You can still get back to this by trying to use that and putting your acceleration in as 0, or you can just keep this on your equation list as well for your quiz and make sure you know it's there. Then, when we solve this equation for our displacement, so the velocity of my Mustang times delta t is going to equal my displacement. So now I can kind of just stick it on that side of the equation. So this is like one long equal sign because I wrote it too far away. My Mustang's velocity times the time equals my Camaro's velocity times time plus 1/2 acceleration plus time squared. So combining my 2 different equations there to make one because I know that my displacement has to be the same for both of them. So then they went ahead. We know our Camaro is starting at 0, so we canceled out that first part. And then they solved to isolate our time value. So what we did here, I'll just walk you through the steps on the slide, is we're trying to get our time separate, but because it's on both sides, it can be a little tricky because anything you do with it is potentially going to cancel out on the other side, and we don't want that to happen. So we're going to move this whole phrase over to this side by subtracting it. So now we have that part subtracted. Can't see one point. You have your 1/2 AT squared minus your Mustang's velocity times time, and it's equaling 0 because there's nothing left on that side now. And then what I can do is I have time on both pieces of my equation, so I can pull it out as a factor. So they pulled out time squared on both of them. Now remember, this is also being multiplied together, so the grouping looks weird because of the parentheses, but we're just multiplying it still, and it's all just still one chunk. What we're going to be able to do is rewrite it having pulled the time out itself. So we had a time squared over here and a time over here. We were able to pull a single time out. It sounds weird to say out loud. And when we do that, what we can do is actually divide by delta t on both sides. And when we do that, we cancel it out. So we kind of lose it, but remember, we still have this one right over here. So with these now gone, I still have 0 equals my 1.45 delta t minus my 14.2. And then what I need to do is isolate my delta t. So I'm going to add the 14.2 to both sides. And then once I do that, I will get 14.2 equals 1.45 delta t, and I'll just divide by my 1.45 to get this guy here. Then when you calculate it out, they get the 9.79 seconds, delta t. And so they're going to meet again after 9.79 seconds. So they first met at 0 seconds, which is kind of what we saw over here. That's where that cancels out is, okay, well, we had one time where they met then. And then our second time is almost 10 seconds later. But we're not done because we need to figure out at what distance they met. So I'm just going to plug that back into either of my equations. The easiest one is that first one. So I had already had it rearranged like this. So I'm going to plug in my numbers. So this is my velocity for my Mustang that it was going at a constant velocity the whole time. Then the time that I calculated, multiplying those two together is going to get my total distance. And if you wanted to, you could technically plug this time in for the other equation as well, if you wanted to prove to yourself that it was right. But you should get approximately, they rounded, 140 meters north when you do that. I guess here, let me just kind of prove that out to you. Because why not, right? Like math, yay. Okay, so I come back here. I now know, let's do it in obnoxious bright green. Okay, so I'm going to look at we just solved it with the Mustang equation. I'm going to go ahead and plug my time into the Camaro equation just to prove that this is what happens. So my displacement is still what I'm solving for. And my starting velocity was 0. So I can actually get rid of that whole first piece. So I have plus 1/2. The acceleration on my Camaro was 2.9. And then my time was 9.79 squared. So once I do that, 0.5 times my 2.9 times 9.79 squared, I get that displacement of 138.97 meters north. So that was just me. You don't have to prove with both equations, but if you're not really sure if your answer is right, you can always double check it. That's one super nice thing about math. Math is just reliable. Like it'll give you an answer whether you like it or not. Okay. I skipped ahead. I skipped through example 3 because it involves the quadratic equation. You can feel free to write it down. However, it's more complicated than I would like to do over remote learning and without having your equation sheets ready for you to have in front of you. So skip example 3 on your notes. That's totally fine. And I will post any updates you need to your assignment based on what types of problems they involve. If you need any help, feel free to reach out to me through email or Google Meet.